Hi, welcome back to my channel. So this is episode 6, and I want to continue the experimentations with my HackRF here. So in the first few episodes, we checked out the behavior of the HackRF as a spectrum analyzer using the Q spectrum analyzer application available for, well, all platform. In this case, I used it in Ubuntu, Linux, but it's also available in Mac OS X and in Windows. So today I want to change direction in a sense and study the behavior of the HackRF as a transmitter or as a signal generator. So I want to see in particular if what is the level of harmonics and spurious emissions that the HackRF produces. One idea I have for the HackRF in the future is to try to make it into a radio, basically a transmitter. So the idea is to connect the output of the HackRF to an amplifier and then use it, for example, to communicate in the ham bands, radios bands. So I mean, just to be clear, I will not do that because I'm not a licensed ham operator. But I want just to check out the potential, the technical potential of that. And in any case, I'm thinking about getting a license. That would be cool to keep learning about these things and experimenting them in real life. Anyway, back to the topic of this video. I want to see what is the output, how clean is the output of this HackRF. So I'm going to just connect it using this cable, which is the cable we used in episode 4. It's a high quality semi-flex SMA cable. And I'm going to plug it into the input of the spectrum analyzer and so observe the spectrum of the output of the HackRF. So before doing that, since the HackRF is just, this is a Chinese clone actually of the HackRF. By the way, I will make a video about explaining the difference between this model and the original HackRF. I forgot to do that in the first episode. Anyway, I don't trust this, the output of this to go into my beloved HP 8591E spectrum analyzer. So I'm going to inline the cable with these components. One, this thing is, we already looked at it in episode 4, is a 10 dB attenuator, and we checked that it actually does its job in the 0 to 1.8 gigahertz bandwidth at least. And this is a DC blocker. So this little component, which I don't know if is visible here. So anyway, it's from a mini circuit. So this is a decent. So it's a piece that has a data sheet and some known performance. But anyway, the functionality of this little device here is very simple. It blocks any DC component on the input. So ideally, the HackRF will not produce any DC component anyway. I mean, it's possible to add a DC component to the signal to activate some external antennas or external amplifiers. So, but this is not active at the moment. But anyway, I want to be super sure about that, adding this DC blocker. Theoretically, anyway, my spectrum analyzer can withstand 25 volts of DC components, so there should be absolutely no problems with that anyway. But just to be safe, I'm going to just use this minus 10 dB just to reduce a little bit the strength of the output. Again, this spectrum analyzer can withstand 30 dB input, so it's not going to be a problem at all. The maximum power of the HackRF, I believe, is 15 dB, so no problems there, but I prefer to be completely safe with minus dB attenuator and a DC blocker. So let me just do that. I'm going to add this. And as a form of extra precaution though, I'm going to attach first the output of the HackRF to my 20 megahertz bandwidth analog oscilloscope, just to make sure things are going as expected and we are getting the expected signal out there, not something weird. Again, I'm very careful. I want to protect my spectrum analyzer as much as possible. So let me try to plug this here. Done. Okay, so okay, so here's not properly connected. So then part of the. Okay, so the connection is performed between the HackRF and the oscilloscope, right? So let me. These connectors are always a source of pain, as you could see in my previous episodes, especially. Okay, now things should be better. Let's hope. Okay, so now let's activate the HackRF, and to do that I created this little script, this little sketch in GNU Radio. So let me just show you what it does. So there is a signal source. This produces in software a sine wave, a cosine wave of frequency 1 kilohertz. And this frequency is going to the HackRF, which is this component here in GNU Radio. And effectively, what's going on is that the HackRF with output this frequency shifted in frequency of FREC here. So this is the output frequency really of the HackRF, and this can be controlled by this slider here, which goes from 1 megahertz to 1750 megahertz, so 1 gigahertz, 750 megahertz, which is basically the limit of my spectrum analyzer, which is 1.8 gigahertz. Okay, so so this is a very simple script, just to have a very basic idea of what the HackRF does in its output phase. So okay, I'm going to run this thing here by clicking here, and now it's running, and let me just add something to the output of the screen capture. So now you should see also right. So let me see. Okay, now we see the slider. The slider is this thing here. At the moment we are outputting one. So I actually have to enlarge it slightly to get. Sorry about these details. So let me reduce the size of this. Okay. So you can follow what's going on at the level of GNU Radio. So at the moment GNU Radio is outputting a signal at 1 megahertz. Okay, and this is shown by this oscilloscope. At the moment we have let's put it 1 microsecond per division, and indeed we are getting about 1 period per division. So this is indeed a 1 megahertz signal as expected. However, if we go here and we put 10 megahertz, you will see that the signal has dramatically increased in strength. So the fact here is that really the HackRF performs very poorly at low frequencies. I think it can be considered, I haven't looked precisely at its specification in terms of output, but I think it performs very poorly at 1 megahertz, so it starts performing better at 10 megahertz. So here we get our 10 megahertz signal, and just to check that things are good, here I'm checking, at the moment the oscilloscope is set to AC coupling, so it's removing any DC. So let me ground the input, and this is DC coupling. So you see DC is equal AC, so there is no DC present in the signal, which is great, which is what we wanted. So now with this oscilloscope I basically check that indeed the signal is okay, it can be inserted in the input of the spectrum analyzer without the risk of damaging anything. So I will just do that now. So first I will close, I will stop the HackRF. So the HackRF is now not outputting anything. And then I remove this from here and connect to the spectrum analyzer. So again, I will make very sure that all the connections are properly connected here. Okay, it's always a pain. Yeah, again, as I explained in my previous video, episode number 5, the majority of these adapter and even this attenuator are very cheap stuff from China. So it's kind of to be expected that they are kind of annoying, and if you don't connect them super properly, things are going bad. But okay, so here I'm pretty sure now that the connection is quite good. So I will open once again the GNU Radio program that produces the output, and so we can start checking its behavior on the spectrum analyzer. Okay, so let me just set a couple of things. Okay, so of course you can follow the output of the spectrum analyzer here, so it's more visible. My camera doesn't work so well, so here it's better. So as a first thing, we can see that now the HackRF is outputting this 1 MHz signal. Okay, but immediately we see that there are some extra signals available. So it's outputting also something around here, 300 MHz. We see some spikes here as well. Also here. So let's here we are at what 50 MHz. So it's a very noisy output at the moment at 1 MHz. As I told you before, it doesn't seem like the HackRF is working very well at these frequencies. Anyway, let's go to 1 MHz just to check it out properly, and let's put a span of 2 MHz. So this is what you get. So you see also this sort of asymmetric response here, where the right part is kind of having more energy than the left part. I don't know. So I would just say that the HackRF is not good at all at outputting at these frequencies, or at the very least, you have to use a filter after the output to clean the signal. Okay, so let's try to increase the frequency to see if the response is any better. So I'm going to put, for example, 10 megahertz. So let's go back to 900 megahertz, so which is the default, so 1.8 gigahertz of span, and this is what we get. So again, we can see a lot of emissions here. There are emissions at again 300 and something megahertz, and so it definitely looks like the HackRF needs some filters at the output. Anyway, yeah, it has to be said that the signal here at 10 megahertz is, so let me find it's the peak with the peak search function. So actually let me zoom it a little. So frequency, let's put it 50 megahertz and a span of 100 megahertz. So with the marker we can see that we have our signal here at 10 megahertz. Perfect. And yeah, there are some harmonics. So namely there is this first harmonic at 20 megahertz. It's about 3 and something division down, so minus 30 dB, which is 35 even, which is I mean, okay. There is the third harmonics, the fourth harmonics, the fifth harmonics. So you get I think we can say 35 dB down in terms of additional unwanted harmonics. Still, I think this requires filtering. For example, if you're outputting this at in the ham bands at 10 megahertz, which is I think the 30 meters band, you definitely need to filter out these harmonics. The HackRF cannot be used directly with an amplifier as an emitter. So let's try to move to 100 megahertz to check out if things improve. So let's move the frequency to let's say 300 megahertz with a span of 600 megahertz. So we have a look. And here it's our main signal at 100 megahertz indeed. And here this doesn't look like an harmonic, right? So it's 321 megahertz, so it's not really an harmonic. The harmonic is, so let me see if so this is, yes, our 100 megahertz. The harmonics at 200 is not present, or it's very attenuated, so this is basically 40 dB down. 4 division down means 40 dB. This is, here it's the position of the third harmonics, but this is also 40 dB downs. Instead we have this 320 megahertz that must be associated just to internal noise of the HackRF. So in this case we get that the unwanted harmonics is again 30-35 dB down compared to the main signal, so minus 30 dBc. Yeah, so let me actually again see the whole spectrum up to 1.8 gigahertz, so we can have a look at the whole thing. So yeah, here we see our 324 noise signal that is added about 30 dB down, in fact even 40. And here there is also the noise present at 50 megahertz. So again, at the very least 30 dB down. So this is something we can say it's kind of consistent. So let's have a look at increasing this frequency to 247. And I'm going just to sweep here with the mouse to see the response more or less. You see, so the noise that we had here is kind of constant, this 320 something, and similarly for this 54 megahertz, it looks like it's constant. So let me just try again. So yeah, you see these noise signals are staying there. Even when I sweep my signal, when I increase the frequency. So here I have this kind of harmonics here that I'm not sure what it is. It could be a mirror image, in fact, of so this is at 1 point. So let me see. If I generate a frequency of just 1 gigahertz, so let me just write it. So 1000 E6, which means 1 gigahertz. As you can see, I'm getting this signal here at 1.5. So let me think what this could mean. I don't know, because the harmonics theoretically is going to be at 2 gigahertz. So I wanted to look if there was some relationship with this 1.8, but it doesn't look like. So I'm not really sure what I can say about this. But anyway, the signal here it's at about next peak, as we can see, minus 30 dB m. And the next, the noise here is at minus 60, so we are a good 30 dB down. Again, it looks like the HackRF is this is the level of quality of the signal. So the spurious emissions are at minus 30 dB down. So let's see how it proceeds by sweeping a bit more. Yeah, it looks like this is kind of consistent. So I'm now reaching the limit of the spectrum analyzer. So as you also can see, the strength of the signal is not constant over the spectrum, so it's quite strong here. So here at 800 megahertz we get our about minus 30 dBm. If I increase the frequency, the signal is going down, you see, and then it's going up again, down. So it's not really calibrated in this sense. It's outputting in an uneven way. So again, just visually here, this is just a first test. I don't want to go into any details here. I just want to have a very first look. I want to see if we can claim that the HackRF outputs the main frequency, and then all the spurious emission are at the very least minus 30 dBc down. So let me just again sweep across the spectrum. So to check if this is the case, so 30 dB, remembers, means 3 divisions. So it looks like here maybe, yes, so this is still probably true. Okay, definitely true here. And yeah, here it's pretty bad, I think. So we have our main signal here at, so peak search, next peak. Okay, so we have our signal at minus 35 dBm, but in this low side of the spectrum we have noise at minus 60. So yeah, it's only 25 dB down. So it's not even true that the HackRF maintains this minus 30 dB with respect to the carrier. Yeah, no, that's not the case. This looks at 800 megahertz, so this is pretty bad. I mean, pretty bad, relatively speaking, of course. Yeah, here it's even worse at 1.75. So again, the signal at 50 megahertz is minus 55 dBm, and instead our main signal is minus 38. Yeah, 25 dB down or something. No, 22 dB. No, sorry. Here it's minus around minus 40, and here it was. Yeah, it's only 15 dB down. So yeah, not good at all. And we have this intermittent signal here. It's changing in power over time at 600 megahertz. So yeah, my conclusion after this first very rudimentary experiment, as just an application of my spectrum analyzer here, I can say that the HackRF definitely needs some filtering at its output if you want to transmit it with some significant power, so to send the output of the HackRF to an amplifier for long distance communications. This is, by the way, expected. This is in the documentation of the HackRF. They strongly recommend to apply some filtering at the output. But yeah, this was just to give you an idea what the HackRF looks like as a signal generator. It's still a very useful tool. And remember, it can go up to 6 gigahertz. So the spectrum analyzer can only visualize up to 1.8, but the HackRF can actually output at 6 gigahertz. And with proper filtering, it's a powerful tool to to combine the functionality of a very basic spectrum analyzer, as we saw in the first episodes, and also for a signal generator. So yeah, this is all for this video. If you enjoyed, please leave a comment if you notice something that could be improved, and I'll see you next time. Bye.